Good afternoon. This is James Smits with Interface H2O. We're going to get started. It's 12:01. We'll keep admitting folks as they kind of join in. Today we're going to host Lance from Momentum Environmental and chat about the preserver and how it's a good application for manhole structures and how we can effectively remove sediment from those waterways on our subdivisions and forebays and how to manage sediment. So my name is James Smits and I'm the president of Interface H2O. We've been in business for 11 years and we are a distributor of stormwater products in Michigan and work with engineers, architects, governmental agencies to remove sediment from stormwater, whether that be in an urban environment or a rural environment. And so we take pride in working with engineers and helping them with solutions to problems in the natural environment. So I'd like to thank you all for attending, and we will be here about an hour, and we will learn about Momentum Environmental and the preserver from Lance. I'll give Lance's bio here. Lance started his engineering career at a large municipal consulting firm in Minneapolis, where he gained experience on a wide variety of water resource projects over his decade tenure, ranging from detailed design to master planning. He was frequently called in on stormwater products and then began to look at how to deal with stormwater, manufactured his own methodology and came up with the preserver as he saw a need for it in the Minneapolis and Minnesota marketplace. During his 5 years there, he became intimately familiar with the stormwater product industry, eventually leading him to start his own company, Momentum Environmental. Momentum started as a consulting firm for stormwater product manufacturers and shortly after forming the research and development for the preserver. We would like to thank Lance for joining us. Interface has been using the preserver for about 4 years now across the state of Michigan. And so we've had some success in implementing that on projects in different locations. So we'll have the chat feature open. So please feel free to answer or pose any questions as we go along. We won't wait until the end. We'll compile all the questions and answers as well from Lance when we send out the PDH certificates in the next day or two, and we'll get going from there. I will turn the controls over to Lance to get started.
Okay. I don't think I have control yet, but hopefully you can hear me. So thank you everybody for joining us today. Appreciate the interest in the preserver. And thank you, James, for the intro. That takes that off my plate. Perfect. So just jumping right into it here on the title slide, what I kind of want to direct you to the main takeaways. And this is for pre-treatment in general. So the preserver can be sold in two ways or used in two ways. And one is as pre-treatment, which is prevalent in Minnesota, but that's evolved over time, which I'll talk about. In new markets and like in Michigan, we still see numeric goals like 80% removal of OK110 or 50% removal of the NJDEP particle size distribution. So we can take our testing and determine what size structure we need to meet those goals. However, by and large, it's sold as a pre-treatment practice in Minnesota, and we'll I kind of talk about it in that regard. And so this main takeaway, and this is for pre-treatment in general, it's a good engineering practice, and it's a good engineering practice because it reduces maintenance costs and it protects downstream BMPs, and in particular with the preserver being a structural, housed in a manhole, usually the last manhole discharging to a BMP. It's also an easier point of maintenance. So that for those reasons, all those reasons, it is a good engineering practice in general, and one that pays for itself over time by reducing long-term maintenance costs. So I don't have control here, so if you can advance the slide, that'd be great. So what is a preserver? Let's kind of talk about that, and then I'll talk about what each component does in the following slides. So it does consist of two components. It does need to be housed in a sump manhole. So in this picture, we have number one, the influent pipe. If you're going to be using a dissipator, you need an influent pipe. So number 4 is our energy dissipator. Number 2 is the outlet pipe, and that we have a skimmer on that. So that's number 5 is a skimmer. And number 3, we're just kind of showing the sump manhole. So sump manhole defined by structure depth below the outlet invert elevation. And typically we're at about a minimum 3 feet sump depth for these. We do see some shallower because it can be retrofitted to existing sumps. So if it's a shallow sump, depending on the pipe size, we can go shallower, but we would recommend probably minimum 3. We see a lot of 4-foot sump depths here in Minnesota. Yeah, so it is flexible. Next slide. So kind of start out with talking about the dissipator, the problem that it addresses, and that's really targeting sediment removal and sediment retention during high flows. So what is the problem? It's sediment, right? Overloading our infrastructure. And you see it in the conveyance systems, like in the left pipe there, and we see it in ponds too. So ponds have been around for about 30 years, and they've started filling up about 10 years ago, and that's when we realized we had a maintenance problem, really. So not that it hasn't been a problem in the past, but it really came to light in our area, at least. Maintaining ponds, once it had to be done, started about a decade ago. Cities primarily were the main owners, and they realized how expensive it was, really, because contaminated sediments also have a high disposal cost, which was unexpected when ponds were originally implemented. So pre-treatment makes a lot of sense for offsetting those costs. Yep, next slide. So another thing that we've seen used as pre-treatment in our area, it's not in all areas, but we have used, MnDOT and cities have used sump manholes to try to address that problem. And a lot of times we put them in the last structure in a line before discharging, whether it be to a ditch or a pond or whatever it may be. So they were trying to capture sediment in sump manholes, and I'll talk a little bit more about the testing that led us to this realization. But the problem with sump manholes is that they can remove sediment. We know that, but the problem is when during high flows, which we're going to be talking a lot about high flows here, but during high flows, that sediment can just be washed downstream, which there's some terminology that's a little bit different in some areas too. I'm going to refer to that as scour when high flows come in. The turbulence resuspends previously captured material and then washes it downstream. So just for ease of talking here today, I'm going to call that scour. So that's what I mean when I talk about that. So that's the problem with some manholes. High flows come and that previously captured material is just scoured out and washed downstream. Next slide, please. So that's what the energy dissipator, the preserver energy dissipator, was developed to prevent primarily, is what happens during that high flow. We want to prevent that scour from occurring. So that is the primary benefit of the dissipator. It was also through testing discovered that it has a side benefit of doubling sediment removals in comparison to just a standard sump manhole with similar dimensions or the same dimensions. So some of the other points of the dissipator is, like we talked about, it's a cost offset for long-term maintenance, an easier point of maintenance. Nearly eliminates the washout of previously captured material. Double sediment removal. The dissipator as well as the skimmer accommodate pipe diameters up to 48-inch. Everything is fully retrofittable through a 24-inch casting, and there's a reason for that, which we'll get into later. But with that said, it is retrofittable, but probably 95% of our installs are for new construction. It's adjustable. This is also unique to the preserver, to my knowledge, but it's very advantageous because contractors are usually putting this in, and anyone that knows contractors knows that they will put it in no matter what. So so whether it's right or not. So we like to give contractors as many of the tools they need to put it in. We like to give them that install flexibility, so it increases the chance that they get it in correctly. So that to me is an important one. So if say a pipe's protruding 12 inches into the structure, they can install the dissipator or the skimmer to where it's supposed to be to function correctly. It's very strong structurally. Our structural design is something we like to hang our hat on, and I'll get into that more in a little bit here. The dissipator was designed to function with or without a skimmer, so that's a nice thing about this too. So when you look at some, whether you call them hydrodynamic separators, some of the other proprietary devices on the market, swirl separators, gravity separators, they usually always have, they're targeting sediment removal. They almost always have a skimming component to it as well, which is usually built in. So the nice thing about the preserver is that both components work with or without each other. So they're designed to work together or alone. So if you feel on your application that you don't need skimming, you don't have floatable pollutants, and you just want target sediment, you can just pay for an energy dissipator. You don't have to pay for the whole structure, which is another nice cost savings. And vice versa, if you are targeting floatable pollutants and you don't necessarily have a sediment problem, you can put just a skimmer in and not have to worry about paying for a dissipator. So it's a nice system in that regard too, very flexible. Everything's third-party verified, full-scale laboratory testing. We also have case studies that are all third-party. That's something that we do ongoing, just because we think the most important thing is proving how it works in the field. Laboratory testing is great for proof of concept and giving you some idea of, how to hit those numeric effluent limits, like 80% removal OK 110. But ultimately, what really matters and what we're trying to get to is removing sediment in the field, right? So that's important as well. Easy to install, access, inspect, maintain. We really tried to look at all aspects. Being a consulting engineer, I wanted this easy to design. As a product developer, I wanted easy for the contractors. I wanted to provide as much information and tools for every aspect of the installation through maintenance to make this just a really easy product to work with. So next slide, please. So just kind of talking about how effective the dissipator is in general. There's a lot of the methodology that we use for this was developed at the University of Minnesota. So look out the University of Minnesota testing methodology. And they tested a whole array of proprietary devices, and including sump manholes. So when you look at a sump manhole, and we're talking about what happens during high flow, it's very important, and I'll get into that more in a bit. But what happens during high flows in any of these structures, right? That has to be a design consideration when you're looking at specifying these or developing a target. Even if you're a regulator, you're trying to figure out, what's the best target for specifying these structures, or what should we be trying to do? High flow has to be a consideration. So what happens during the big storms? And in a sump manhole, we already talked about this. we get scour of previously settled solids, and the way that this was measured in this testing protocol is what is your effluent concentration. You preload the sump with sediment, you run high flows through it, and then you're seeing how much on average is coming out at that high flow. So the highest flow tested in the laboratory for this protocol is about 16 CFS for most of the structures. The Sump Mantle is 16 CFS, and the effluent concentration range from 200 to 600 milligrams per liter. So if you kind of look at it at an example, Swirl Separator, which is the next, if you click here. So this is an example, and if you're familiar with these, this is a downstream defender. This is one of the devices tested there. And this is all public knowledge, but the devices that were tested there are ones that a lot of you may be familiar with: downstream defender, storm scepter, vortex, CDS, V2V1. Familiar with those? I think it said storm scepter already. Sump Mantle. So, and there's more than that too. Cyclone, EcoStorm. There's a whole bunch of them. So a lot of ones that you're probably familiar with. But so swirl separators. The benefit of swirling water is increasing removal efficiencies, and they do a good job of that. So swirling water at low flows is a great way to increase the particle travel path, give it a longer amount of time to settle out of the water. So you can increase sediment removal efficiencies. You can also target smaller particles that wouldn't otherwise have time to settle out in a sump manhole. So it is a great strategy for increasing removal efficiencies. However, the downside of swirling water is that it can greatly exacerbate scour at high flows. And this is something that isn't really tested, with the exception of this University of Minnesota testing protocol. A lot of laboratories just didn't have high flow capacity. So there's other testing protocols out there that are very popular. And if you're a regulator, and I know this has started to come into Michigan, like NJDEP testing protocol. I really like the sediment removal side of that testing protocol. However, I think the scour testing is insufficient to reflect real world conditions. And I really think it's just because the laboratories don't have the flow capacity to test to what would be a more realistic flow rate. So that's where, a lot of these swirl separators through NJDEP are approved for online use. Whereas if you look at the University of Minnesota testing, they should not be placed online because they'll scour at high flow rates. So next slide. Oop, too far. So now you look at that compared to the test results for the preserver energy dissipator, with or without the skimmer. We saw 15 milligrams per liter. So one thing you'll see is it's very consistent versus a sump manhole. Sump manhole at the range, you're kind of getting this 200, 600 milligrams per liter, but consistently low. So 15 milligrams per liter. And kind of talking about, and these are all at 16 CFS with same structure dimensions. So when you look at this and talking about NJDEP, if you're familiar with it, their scour testing protocol is for you can't exceed 20 milligrams per liter effluent concentration. And that's at a flow rate, the highest tested flow rate that for the best performing device on the market currently is 3.6 CFS. And they just have to be below 20 milligrams per liter. And you compare that to the preserver where we're testing to 16 CFS and we're below that 20 milligram per liter. So there's a big difference in that scour suppression ability of the energy dissipator versus some of these other devices tested at NJDEP per that protocol. Next slide, please. So onto the skimmer. So skimmer, there's a lot of skimmer options on the market. They've been around for a long time. They all function the same way. They're really just trapping floatable pollutants, whether that be trash, oils, grease, things like that, cigarette butts. We do see a benefit to organics. A lot of times leaves can be trapped in the sump. If it's quiet enough, like with a dissipator, they'll float initially, then become waterlogged as they settle to the bottom when the storm subsides. and we find a lot of organic material in our sumps and the preservers. But so that's the type of thing that we're looking at with skimmers. We're trying to prevent what you see on the right there. You can click to the next slide. So the benefit of skimming in general, really, and the preserver functions the same way. Like I said, it forces water below the water surface, trapping anything that floats on the upstream side of the skimmer. So a lot of the same benefits as the dissipator. Accommodates 48-inch pipe sizes. Every one of our skimmers is designed to fit through a 24-inch casting, so they can be retrofit. Very strong, structurally adjustable. Will function with and without the dissipator. Has the same third-party verified performance. There is more to a skimmer than a dissipator, as you can kind of see in that upper right-hand picture, that the frame that we put together there. So it is still relatively easy to install, but there's a little bit more to it. And I'll kind of talk about why here in a second. But we can go to the next slide. So talking about the structural capacity, this is an example of what we did for our skimmer, and really to determine forces on both components. We use computational fluid dynamics, and that's because, I mean, we were able to test to 16 CFS in the laboratory, and that was for a 24-inch pipe in and out. However, we accommodate 48-inch pipes, and our maximum allowable flow on a 48-inch pipe is 175 CFS. So that's not something that is really feasible in a laboratory environment. So we kind of have to go to this level to determine the loads that we're seeing on our components. But we did go through this exercise. It's a great exercise. All of our inputs are very conservative. For example, when we do our dissipators, we assume there's no perforations in it. It's just a solid sheet. So all the force coming from the inlet is fully transferred to our dissipator and the brackets and the connectors and everything like that. So, so we have very conservative structural design, and a skimmer in particular is very, there's a lot of structural design that needs to go into it. It sees higher forces than you have at the inlet. And if you look at the computerized image on the left here, those difference in colors of each one of those spheres represents velocity. So your forces in your water is a function of velocity squared. So as you can see in this diagram, there's a force from the influent water, and this would be worst case when the dissipator is not installed, right? But if you have a force from the inlet coming right to the face of the skimmer, you're getting that force. You're also getting a suction force from the backside, which has much higher velocities coming out. So this skimmers are also something, so ultimately this is a water quality device. The last thing we want is to create a flooding problem with any device that you're specifying, right? But we as a manufacturer place that very high on our list. So everything's very conservatively designed since inception. No damage or failures to the preserver. So that's something we're very proud of. I know that's not the case for all of our competitors. So when you look at the right here, that skimmer frame, all stainless steel, hardware brackets. These guys just use it as a ladder, and that's just a small portion of the capacity of the skimmer. This one in particular is a 36-inch pipe that accommodates 100 CFS. The force we calculate on that, we're over 11 tons of allowable force on this before we even hit our factors of safety. So very, very conservatively designed. Sleep well at night when the big storm comes. So next slide. And this is what we're trying to prevent. So this is a project that was brought to us. This is a more common, skimmer that's been around a long time, manufactured out of fiberglass. This particular city was having a problem because this is by a park and they get trashed, so they wanted to have a skimmer. But they realized that over time they were getting flooding in the street at very small storms. So when they look down in there, you can kind of see how it's caved in. And so the skimmer has failed and is probably resting against the outlet pipe. So And there's a couple things to point out here too. If you just hit the next slide, we'll have another picture pop up. So another thing about the skimmer and full transparency, we get some comments too, like when you get a big storm, can't floatables overtop our skimmer, and it can. So that would be a downside of our skimmer design in comparison to one of these traditional ones. However, access for maintenance and inspection, we get a ton of good feedback from typically cities that are going out there and inspecting these. They really like that they have the access and maintenance from the top. They can look in there, make sure everything looks good. Also, if you have a closed top like on the left, I wish, inspectors could be out 24/7 on a job site, but they can't. They usually come through with punch lists and say, yep, the skimmer's been installed. But when you look at the skimmer on the left, you have no idea where the outlet is. It could be an inch away from the face of the skimmer, which is not a good install, but it would look perfect when you go out and look at it. So there's definitely some advantages. So the other thing is being fully retrofittable. What does the owner of this failed skimmer on the left do now? They have to cut that out, and they either don't put a skimmer back in, but they want a skimmer there, right? Or they have to take the top slab off if they want to remove it in kind, probably fix the outlet pipe, cut it back, do the restoration, including pavement from the street that it's under, versus a preserver skimmer. Real easy, cut out the existing one, everything's retrofittable. All you have to do is back it out, get the guys in there, you're in and out probably in a morning, and the job's done. So much lower cost without those restoration costs in there. So if you ever run into any of that, it's nice to have that retrofittable aspect to the preserver. And one thing I want to mention about that picture too, we get this comment, I've given this presentation before, but we don't use structures that size. That's a huge structure, right? And this is not a typical install. Our typical install is by and large a 4-foot structure, 4-foot sump, typically 3 or 4 foot sump, and a 15-inch pipe in and out. So this is a rare install for us. We do get bigger components, but like this is 36-inch in and out in a 7-foot diameter structure. And I just really like this picture because the preserver is retrofittable. Typically what contractors do is at the end of their project, instead of putting it in when they have a 4-man crew and equipment on site, after they move their equipment, they'll send a couple guys back and they'll put everything in through the castings, and they'll install everything with 2 guys, which is another cost savings for them. And get that done that way, less expensive. So all of our pitches are typically through castings. This is probably the only install I've been to where the top side was off. So it was really a great photo opportunity. That's why you're seeing that so much. So just a little bit of the story on how it was developed, because I do think it's interesting. So MnDOT, it really started with MnDOT becoming regulated under the MPDS Phase 2 requirements and became an MS4 in 2003. And what they did is, they're supposed to show that they're providing as much treatment as possible, water quality treatment of stormwater. So what they did is they said, well, we already have a bunch of ponds, which they can estimate removal efficiencies for. Lots of programs on the market for that. But they said, we don't have a way to, and their reporting for that has to be an annual load of sediment removed. And when you have requirements like we had, which is similar to Michigan now, 80% removal of OK110 at a specific flow rate. There's no way to get to what's my average annual load removed in this structure. Same thing with, NJDP requirement is kind of an annualized analysis. So that one probably worked a little bit better. But in general, what they wanted to do was have testing methodology. They wanted more than that, than what was on the market. So they approached the University of Minnesota to just start from scratch. Say, what do we need to get to this end goal of what we want, which is has to be very flexible testing methodology. We have a lot of, just say, storm scepters in the ground, as well as other proprietary structures. But not only do we have 4-foot storm scepters, we have 6-foot and 8-foot storm scepters, but we only want to test one of those. So they needed something that predicted removal efficiency on an annual basis, spit out a load of sediment removed, pounds of sediment removed per year. But it also had to be a similarity equation where they could apply that and get accurate estimates for a 4-foot structure and an 8-foot structure, 6-foot structure, any size structure, right? And varying pipe sizes too, different pipe sizes coming in and out if that affects treatment. So U of M took a fresh approach to what is the best way to model these structures in general, how to test them and predict removal efficiency. So they said basically two things. You can click ahead a couple clicks here. They said two things. Number one, how well does it remove sediment? How well does it remove sediment during low flows? And number two, how well does it retain that sediment during high flows? And two separate functions were created for both of those scenarios, and then they're married together in either a program or a spreadsheet using historic rainfall data over a period of time, and then averaged out to get an average annual removal efficiency. So it's taking, local rainfall data and applying it over time and saying what would have happened over the past, say, 12 years. That's the time frame I like to use. 12 years, if we ran all those historic rainfall through this device and then averaged it out, how much sediment we removed per year. So it's a very accurate way of doing it. It's the most accurate way that I'm aware of on the market today. And we see this in our case studies too. We see that what we get in our case study is reflected in the testing protocol. It's been more accurate than say, I hate to pick on NJDEP, but just because they don't test a high enough flow rate, we see those devices that have been approved for online use in NJDEP. But when you go to check them, we know we get high flows. We have intense storms everywhere in Minnesota as well as Michigan, everywhere but the West Coast, right? And we see that a lot of times, sometimes those structures are empty if it's right after a big storm. So what happens during those high flows is very important. So, and just to continue on, so that is where we get the information for standard sump manholes, because once they went through that process through several years, as you can see, of testing proprietary separators, they said, well, now we want credit for our sump manholes. And that's where the University of Minnesota went ahead and tested sump manholes. They said, well, we can remove sediment, but we have a tough time holding it during the high flows. And that's where the preserver was born. It had to be, that's why it's retrofittable, because, somebody wants credit for their sump manhole that's in the ground. You need a way to get something in there that prevents that scour. And that's exactly why it's retrofittable, exactly why it was designed to target or suppress scour during high flows. So we developed the preserver. It's gone through full-scale testing. We use that University of Minnesota methodology, but we did it at Iowa. Iowa has a really great hydraulics laboratory and set up there. They really operated like a business. They don't use students. So time was of the essence when we tested. We wanted to get the product on the market as soon as possible. So they really approach it in a kind of a professional manner and have dedicated staff that work on it until it's done and they get it to you on the due date, which was appealing to us. So, but really, I was really impressed with them. And they brought some things to the table that we improved upon the testing methodology, the accuracy of it. For instance, when we did our scour testing, instead of weighing the entire structure with load cells, which becomes very inaccurate because you have to weigh the concrete as well as the water and the sediment in the structure. So if you're talking about scouring out just a pound or two of sediment, that becomes fairly inaccurate. So we used some lasers that they had. So we would decant as much water as we could without upsetting or disturbing the sediment pre and post testing, right? And then we get a 3D surface with a laser, and they had software that corrected for refraction for measurement through the water. Very pretty cool stuff. So great laboratory anyway. So and that testing meets all current ASTM standards for separation devices. You can go to the next slide. So hopefully this comes through. It's a video. And if this doesn't, this video is on our website. But it's a great visual. Both videos are from that full scale testing. The one on the right, this might be a little confusing because flow is going the opposite direction too, but the one on the right, that's flow is coming from the left to the right from the inlet. And you can kind of see that high energy flow jet. Both of these are taken at 12 CFS, so just shy of the maximum flow tested of 16 CFS. But you can see how the dissipator really changes the flow dynamics in there. So we are doing two things with the dissipator. We are dissipating energy as it states, also controlling the flow dynamics. So we're really taking, instead of the flow going straight from the inlet to the outlet in that flow jet, we're really spreading it out in the manhole by using that kind of arc shape of the dissipator and directing flow from the inlet around the structure. That slows the water down, as you can see. It really keeps the sump very quiet. So, so just summary of that, we talked about most of this already. So our primary goal of eliminating scour, we tested to 16 CFS. Preserver was less than 15 milligrams per liter on all tests with and without the skimmer. Sump Mantles, 200, 600 milligrams per liter, and Swirl Separators up to 3,000. We also doubled sediment removal, and we see this not only with our laboratory testing, our flow-based testing. We see it when we run it through our calcs in comparison to a standard sump mantle, same dimensions. And then we see it in our field observations too. So it's really gone through the ringer. If you're new to the preserver, this is our 7th year of selling it. So it's well proven. It's got a fantastic track record. So like I said, we do see it being sold as pre-treatment primarily, but we can meet with this testing that we did. We can meet and predict basically any target, numeric target. So that's a nice thing about the methodology that was developed by the University of Minnesota. So it's a dimensionless equation that accounts for particle settling velocity, 2 structure dimensions, usually diameter and sump depth, and then your flow rate. So it's relatively simple, but all of those measurements cancel out. It's dimensionless. So we can predict removal efficiencies for varying structure diameter, varying particle sizes or particle size distributions, varying flow rates, and then we kind of went above and beyond. They modified their original removal efficiency to include the effects of inlet velocity, so we can actually predict differences in removal efficiency and sediment retention during low and high flows with varying pipe diameters that cause different velocities into the structure. So it's a very robust equation, but also very flexible and accurate. We find it to be very accurate with what we see in the field. So, so this is an example of something we put together for OK110 removal efficiencies, 80%. So these would be structure sizes that we'd see for that. You can go to the next one and talk a little bit more about the next one. And this is our NJDEP tables. So we do the same thing, use the same testing results to put together these removal efficiencies. And I'd like to point out here, so the best NJCAT swirl separator on the market today has with their 4-foot diameter unit, has a treatment that's MTFR's manufactured treatment flow rate. And they're trying to target 50% removal on an annual basis. So that equates to a target of 1.8 CFS during it's calculated from a 1.25 inch storm. But anyway, just the flow rate, best flow rate out there is 1.8 CFS. So their scour prevention flow rate to not exceed that 20 milligrams per liter is twice of that. And that's what it was tested to. So 3.6 CFS. And now you look at what we have in the right column there for scour prevention flow for that 4-foot, we're at 12.6 CFS, which is, well, on average, instead of 2 times the treatment flow rate, we're about 8 times the tested flow rate. So there's a big difference when you're really targeting that scour prevention and you're testing those higher flows. And then the allowable peak flow down below that table, that's our structural capacity. And that's our allowable peak flows prior to adding our factors of safety. Next slide. And so we do have a design spreadsheet that uses that information. This is our annualized design spreadsheet. So you have, in this example, where it says you can change the device. So we have all devices that were tested using this protocol in there. So it's a great comparison tool. We can adjust, as you can see, diameter, sump depth. You can dedicate a portion of the sump to pollutant storage if you don't want to have that count towards your removal efficiency. Inlet, outlet diameter, local rainfall data, your drainage area info, percent impervious, time of concentration, right down the line to what's your specific gravity of your gradation, varying gradations, what's your runoff concentration if you want to play around with that. It's a nice tool, and it's going to tell you your annualized load removed, and that's our ultimate goal here for MS4 is really that's the data they need. So you can go to the next slide. And this is available. It's not downloadable from our website right now, just because there's some proprietary information in there. I have to do a little bit of more referencing before we put it in there. But if you're interested in taking a look, we'd be happy to share it with you. So like I said, we can target specific removal efficiencies of specific particle size distributions. But what happened in our area, once we went through all this testing for the U of M, and people discovered that you can actually take a sump manhole, add a dissipator in it, and it's going to function as good or better than these other proprietary structures on the market. And it's also a fraction of the cost. What we saw over time is our market evolve from these specific, like 80% removal OK110 targets to this is a good pretreatment practice, and pretreatment is just used, one of these pretreatments used upstream of our BMP essentially. And so what we saw is instead of having just a treatment structure, say at the low point on a roadway, where you couldn't get pipe back to your pond, say, that would be an example where we would have historically used an HDS unit to just treat as much as we could before discharge to the creek that was at that low point. Whereas now what we see is we'll use a preserver there, but we'll also use a preserver in the last manhole that discharges to the pond that's upstream, or last couple manholes that discharge to the pond upstream. So that's where I think that this is just a better use of a gravity separator. A gravity separator has, limited ability to remove pollutants, really. I mean, we're targeting sand-sized particles, essentially. You have a limited amount of volume to treat water in. So we're trying to do the best we can in that space to maximize removal efficiencies and hold on to what we've removed until it can be cleaned out, right? So to me, if you're targeting that type of pollutant level, right, we're trying to get the big stuff out, then that makes perfect sense as a pre-treatment practice versus a standalone treatment structure. So it can be used that way. If you don't have another option, that's great. But if you really look at it, kind of looking at a big picture, how it performs, say, compared to a pond or an infiltration basin, the level of treatment that you get from a treatment structure just makes perfect sense as pre-treatment. So that gave designers in this area, because of the lower cost. So now instead of specifying at one spot, historically, they're typically, we've seen about a 4-fold increase in treatment structures in the area just because they're being used as pre-treatment. They're more affordable, so engineers can use them more prevalently and probably better as they're better suited. But so what we've seen over time is cities who are doing most of the maintenance realize the benefit of pre-treatment before anybody else, and the cost benefit especially. So they said, oh, this is an easy point. We need to make an easy point of maintenance. We need to reduce these costs that we're getting for these ponds. And they started implementing pre-treatment. They were the early adopters, really. So they started using this, and it worked its way up. The regulators said, hey, this is great. This is a great way to enforce maintenance. Instead of telling someone they have to go clean their pond out for $100,000, it's way easier to tell them they have to go clean out their pre-treatment structure for $200. So the regulators really like that aspect of it. And then eventually the state decided it was a good idea too. And every one of them has a different reason though. So the state said, we want the waters of the state being protected to the greatest extent possible. And to do that, we need all of our BMPs that are designed to do that working as good as possible. So pre-treatment helps them to work better. So it's very interesting. So this would, I mean, the state was the last one to have a pre-treatment requirement, and that was summer of 2018. But they did, when they did adopt it, they did a really great job of kind of saying why. And I'd like to read this small snip out of here. So they say in many applications, for example, infiltration or stormwater ponds, the BMP would not be properly used if pre-treatment is ignored. The simple reason for the use of pre-treatment techniques is the necessity to keep a BMP from being overloaded primarily by sediment. Simple, right? that sums it up pretty well. So, and just for an example here, and I'm not saying preserver is the only pre-treatment option either. There's a lot of pre-treatment options. So example, in this pond, you can do a forebay at the inlet to the pond, but what you end up having is you have berms to create that forebay that eats up volume of your pond to meet your pond design requirements. So you'd need more space. We very rarely see anybody eat up real estate to put a forebay in a pond. So that's almost, I don't even know if I've seen a forebay in a pond around here, to be honest with you. So developers barely ever give up real estate for things like that. So they really love a structural pre-treatment device like the preserver. It's used prevalently around here quite a bit. So just an example, you see the catch basin in the foreground here. Just say on average, a preserver removes 50% of the sediment that comes through on an annual basis. That means they're maintaining that pond half as much and the high costs that go along with it, right? So you can see how it makes sense from a financial perspective, from an ease of access perspective. And like I said, just it's a good engineering practice. As I alluded to before or mentioned before, we do have a monitoring program. We have two more that we have, just have to finalize. These three are on our website. I encourage you to go check it out. They're a wealth of information. Everything's third party. What we do is just go measure sediment depths after every inch of rain, cumulative inch of rain, and see how sediment's accumulating through the year. And then we also, at the end of the year, do one composite sample from the sump, have that sent to a lab. This is all third-party measurements, and then chain of custody is maintained from our third party that takes it directly to the lab. So it's all really great information. And what we want to see is that it's working, and that's what they show. So if you go to the next slide, one more quick example. We do have a shallow option. So this is something, we did not test this in the laboratory. So this is a project we had a couple of years ago, and I'd like to take credit for it, but a local engineer actually designed this because he had 2-acre commercial site that was draining all to one side of the property, and he needed a way to pre-treat it before it went into a large infiltration basin that ran the whole, that low side of the property. So he ended up designing this shallow structure. We did a special dissipator design for this. Eventually did a skimmer design for it as well. The skimmers were not installed in this project. He was just looking for sediment removal. But each one of these accommodates over 5 CFS in our area. That equates to a 10-year storm, 1 acre for a 10-year storm. So that's what he was kind of targeting. So it's a nice design. It's a nice option. There's other shallow pre-treatment options on the market. They usually treat a fraction of that area, about a tenth of the area. And they also are supposed to be maintained after every storm because they're relatively small structures. So you're supposed to inspect and maintain them after every storm. We all know that never happens. This has all the same benefits of the preserver, usually going out once a year. You could add some depth to this and size it so you have to go out there every 5 years if you want to. So there's a lot of nice design flexibility. All the benefits we talked about the preserver are here. And what we did is we did this as an example study too. We monitored this location for a year before we released this design to the market, just to make sure, because we didn't test it in the laboratory. We want to make sure it's working. And if you click forward, we do have results from that. Oh yeah, preliminary. Oh, sorry, go ahead. That's good, we can skip that. So this is typical of what we show in our case studies. And so the middle lines you see here, we have those two structures. They're plotted out. That's the average sediment depth instead of the solid line. The blue vertical lines, that's rainfall, historic rainfall data. And the dashed lines are the high and low measurements from within the sump. So you don't have a sediment settling evenly. There's it piles up usually by the inlet. And, that's kind of what you're seeing with that. So overall, though, what we want to see is a trend of increasing sediment depth, right, over time and retaining that throughout the year. So, and that's what we see in all of our case studies. And that's just really what you want to see, right? You want to be able to get to the end of the year. Typically, people are maintaining at the end of the year or waiting through the winter. We actually recommend waiting through like seed fall or making sure you get all the leaves off the roadways in the springtime. That's it. Before your big storms come, that's the perfect time to go and maintain these structures. But that's what the preserver allows you to do. Holds all that sediment in there for maintenance. So, and then just one more thing to touch on here. Last slide. Or going through these. So we have a bunch of information on our website. I encourage you to go check that out too. If you are watching this and you want to maybe introduce the preserver to somebody else, we have 3 videos on our website. If you click forward here, Ben, 3 videos on our website that will get people up to speed really quick. Each of them are about 1.5 to 2.5 minutes long. So take about 6 minutes of their time to really get up to the speed on the preserver in a short amount of time. We also have a lot of downloads if you click forward, a lot of resources. Miscellaneous information at the top there, just like brochure, example installation, things like that. Our guarantee is on there. Design tool, we have manhole sizing charts to make sure that the angles of the pipes coming in and out, size of pipes and everything can fit into a certain size structure. Just mechanically, is everything going to fit in there? Specification, case studies, install, maintenance guides, and videos. A lot of good information on the website. And then last, and I alluded to this already. If you're new to the preserver, we've really done our homework on it. It's been on the market a good amount of time. We have an excellent track record. If you're interested in specifying it, using it, it's not something you have to worry about being a guinea pig on. There's a lot of installs in Michigan. And if you're on the fence, I'm sure the interface guys would be happy to point towards something you can go take a look at. And that's it for my presentation. So we've got some time for questions.
Good. Thanks, Lance. Very great information. Yes, so from Interface H2O's perspective, we had been involved in stormwater quality units in the past. And we had connected with Lance about 5 years ago and saw the benefits from all that are involved from a manufacturing perspective of the ease of putting the preserver in an existing manhole that's made day in and day out, which then gives us a cost-effective option for construction sites. And so 5 years ago, we went on this venture with Lance, and we have units in Kent County, Ottawa County, other parts of the state of Michigan as well, whether they be commercial or residential subdivision type lots. So yeah, and we look forward to helping you in design and implementation of them throughout the state of Michigan. So if you have any other questions, you can, you see my contact information, jsmiths@interfaceh2o.com or lance@momentumenv.com, and we can help you out in sizing and get you the needed information to help you out with your project. So thanks again, Lance. There's no questions in the chat. So with that, look at that. We're 1 hour and short. And so thanks again for bringing it to us here in the state of Michigan.
My pleasure.
Thanks everybody for attending, and enjoy your Thursday afternoon.